This is lecture D for Unit 11, Organic Chem. We're going to continue talking about different substituted hydrocarbons. So we've moved on to aldehydes. Aldehydes have one oxygen, and it's held on with a double bond, and it has to be at the end of your carbon chain. If you were naming it, it would be on carbon number 1. Remember that that means it can be at either end. So your aldehydes could look like this, or you could have it at the very beginning. Either way, it's on carbon number 1, so that gives it the general formula. Your carbon chain, carbon, double bonded O, and an H. It has to be at the end. The smallest one, of course, only has one carbon, so meth. The ending for an aldehyde is -al. So methanal, one carbon, has a double bonded oxygen on carbon number 1, and then hydrogens, so that this guy has 4 bonds altogether. Methanal goes by the common name formaldehyde. That's the one that we use as a preservative, mainly for embalming bodies and long-term storage of specimens. It's no longer used for dissection specimens because they discovered that formaldehyde was a carcinogen. That means it has cancer-causing properties. Aldehydes are made from primary alcohols. So primary alcohols are one where the hydroxyl group is at the end of the chain. It's on a carbon that's attached to one other carbon. So we oxidize it, and we end up making our aldehyde and water. This alcohol, 1,2 carbons, would be FANOL, anol, because it's an alcohol. The aldehyde, 1,2 carbons, is F, and the ending is anal because it's an aldehyde. Methanol becomes methanal. The carbon chain stays the same in these organic reactions. The only thing we're changing is the functional group. So if I were to ask what alcohol our methanal was made from, you would tell me it was methanol. The number of carbons stays the same, just change the ending. Ketones look similar to aldehydes and are often mistaken for aldehydes because ketones have one oxygen as well. It also has a double bond, but this time it has to be in the middle of the chain. That means the smallest ketone you can possibly have is propanone. The ending for a ketone is anone, prop meaning 3 carbons. Prop, 1, 2, 3 carbons. Anone is a ketone, double bonded in the middle. Sometimes you will see this also called 2-propanone because unless it is in the exact middle like this and there's no other choice, we have to put the number with the ketone to tell me where the double bonded oxygen is. So if I had something like this, I would count the carbons, 1, 2, 3, 4, 5, 6 carbons altogether. That's hex. The ending for a ketone is anone, and that double bonded oxygen is on carbon number 3. Remember to count from both sides, 4 from this side, 3 from this. It has to have the lowest number. Be careful that you're not putting a hydrogen here on the carbon with the double bonded oxygen. Carbon can only have 4 bonds. So the general formula for a ketone then is going to be carbon with a double bonded oxygen, carbon chains on either side. They use a prime to let you know that these chains do not have to be the same size. For example, in the 3-hexanone, the chains are not the same size, 3 carbons to one side of it, 2 to the other. Our propanone, the smallest one, is also called acetone, and it's the one in nail polish remover, and we've used it a number of times in labs. Ketones then, also like aldehydes being made from alcohols, but in this case, instead of a primary alcohol, it's made from a secondary alcohol. In a secondary alcohol, the carbon that has the hydroxyl group on it is somewhere in the middle of the chain. For example, this one, which we would call 1, 2, 3, 4 butanol, and it's on carbon number 2. So when we oxidize this and it turns into our ketone, the number is going to stay the same because we're just going to take off the hydrogens. that oxygen is going to double bond on instead of being single bonded on. Number of carbons stays the same, but instead of enol, it's going to be enone. So 1, 2, 3, 4, double bonded oxygen on carbon 2, and your hydrogens. And of course, we're also making water. Again, the only thing that changes is the ending, not the number of carbons, and not the location of the oxygen. So our 2-propanone must have been made from 2-propanol. Moving on to ethers. Ethers are going to be 2 carbon chains held together by an oxygen. So the functional group and the general formula for ethers are O, R prime. So these R's have to be carbons. Carbon chain, oxygen, carbon chain. Really, it's going to have this bent shape because of the angle of the bonds on our oxygen. Diethyl ether, di meaning I have 2 sets that have 2 carbons each. It's a branch, so that means I have an open bond here in the middle. I have 2 of those with their hydrogens all around. Each of these carbons in the middle needs an extra bond held together by the oxygen. Everybody has the correct number of bonds. We don't call this ethyl ether, we say diethyl ether. If you look at your reference table, the example that they use there is methyl ethyl ether. So ether, it's an oxygen holding 2 chains. A methyl chain is 1 carbon, an ethyl chain is 2 carbons. So I have methyl ethyl ether. Whenever we name these guys, split them at the oxygen, name the 2 chains, string that together. Always put the smallest first and then the largest second, no matter what order they're in when you look at the molecule. So if I had something like this guy down here, 4 is butyl, 1 is methyl. So when I name this guy, it would be methyl butyl ether. They're made by dehydrating 2 primary alcohols. So let's draw 2 alcohols. If I'm going to dehydrate it, I'm going to remove water. So if I were to remove a hydroxyl group and remove a hydrogen to make my water, that's going to leave me with 1 chain that has 3 carbons and 1 chain with just 2. So if this is propanol and this is ethanol, my ether over here is going to be ethyl. I change the alcohol ending to a branch ending, propyl, and ether. So if I ask which alcohol methyl butyl ether were made from, it would be methanol and butanol. If I wanted to know what alcohols this diethyl ether was made from, it would be 2 ethanols. Again, we're just changing the endings. Esters have the general formula COOC, and the structure is going to have a double bonded oxygen and then an oxygen and another carbon chain. It's super important that these are both carbon chains on either side of your oxygens. They're made from an acid and an alcohol. So when you look at the ether, this first half came from an acid, the second half came from an alcohol. If you take an organic acid and an alcohol and you dehydrate it, so you remove the water, we're going to remove the hydroxyl and we're going to remove this hydrogen. That leaves us with 1 piece that looks like this and your carbon chain from the alcohol. We put those together to make your ether. When we name it, the part that came from the acid is going to be the ending of your name, and the part that came from the alcohol is going to be the beginning of your name. So if I draw an example one, when I go to name this, I split it where the singly bonded oxygen is. I name the branch here, so 3 carbons is prop. It's a branch, so YL, so propyl. I look at the part that came from the acid, 2 carbons is S, and the ending for an ester is enoate. So this is propyl ethanoate. We can go back and look at which alcohol and which acid esters were made from. Propyl ethanoate, the alcohol must have been propanol, and the acid must have been ethanoic acid. We're going to split them. Be careful if they draw these things backwards. Sometimes your ester is going to look like this. If I were to name this, I'm still going to split it where the singly bonded oxygen is. 1 carbon is methyl. 4 carbons is bute, and the ending is enoate. So this is methyl butanoate. The alcohol it was made from must have been methanol, and the acid that it was made from must have been butanoic acid. But it's going to look weird and a little different from the reference table because they will sometimes draw the structure mirror image from how they draw the general formula on reference table R. Amines and amides on the very bottom of your reference table. Amines, a nitrogen that has 3 groups substituted onto them. They can all be different. They could be a hydrogen. One of them could be a hydrogen or 2. At least one of these has to be a carbon chain. The amide, you're going to have a chain, and the carbon attached to the nitrogen has a double bonded oxygen. There has to be a hydrogen on the nitrogen and another carbon chain. The ending for amines is amine. The ending for amides is amide. They don't show up that often, but where they do show up and it gets tricky is in these things that we call amino acids. So if you see a structure that looks like this, students often get confused because they see the nitrogen, they see the double bonded oxygen, and so their first reaction is to say it's an amide. But there's this extra oxygen here. So if we look closely, this isn't just an amide, this is a COOH. And COOH is the functional group for an organic acid. And this carbon right here next to the nitrogen doesn't have the double bond on it. So this can't be an amide. This has to be an amine, and therefore we have an amino acid. Watch out for this one. It can be a little tricky.